Okay, welcome back. We are talking about something, I think. Let's see, chapter 7 we went back to. And in chapter 7, we started talking about energy, kind of the first law of thermodynamics. We talked about obviously some important parts of energy and processes. Again, an exothermic type of process is where heat and energy is released. Endothermic type process is where we have heat and energy absorbed. I think we looked at some energy sort of diagrams as well that sort of represents each of these. And that's energy, reactants to our products. This would be a exothermic sort of reaction. Again, reactants are higher in energy than products. In order to get there to the products, energy has to be given off overall. We also saw our endothermic, which looks a little bit different. Our products. Here, this would be again our endothermic reaction. Reactants are lower than energy than our products. So again, in order to get there, energy has to be put in. We talked about some other parts of this, I believe, as well. The hill that the reactants have to climb to get to the other side is the activation energy. And that really is the minimum amount of energy required for a reaction to take place. Here for our endothermic reaction, we're looking at this here as our hill that it has to climb. One way that energy is sort of really displayed in equations and in reactions is through our delta H, which is our change in enthalpy. And very commonly, the way that we calculate the delta H for a reaction is basically we take the delta H of all of our products and we subtract it from the delta H of all of our reactants. Remember as well, these are values that you typically look up in a table. To do this, you also need to take into account the coefficient in the balanced equation and multiply the value that you find in the table by that. So again, if you had like 2A goes to 4C, the delta H for this reaction would be 4 times the delta H value for C that you'd find in the table, minus 2 times the delta H value that you'd find for A in that table. And again, we want to take products minus reactants. As we talked about, energy along with some other things are what are considered state functions. And when we have state functions, really the only two important things is where you start and where you end. And in a chemical reaction, obviously, where we start is our reactants. Where we end is our products. So oftentimes we take our products minus our reactants. Now, typically speaking, when you calculate a delta H value or just energy in general, if the delta H value is a negative number, that means that it is a exothermic type reaction that's taking place. If you calculate the delta H and it is a positive value, then you are looking at an endothermic type reaction. On our energy diagrams here, the delta H is really the energy difference between the reactants and the products in this case. And as you can see here, when we would take our products, which is a smaller number, minus our reactants, which is a larger number, that will yield us a negative number in this case. Here, our delta H of the reaction, again, our products minus reactants. So when we do our delta H of the reaction, our products are actually a larger number minus a smaller number, and that's going to get you a positive number here. So typically speaking, positive energy values endothermic, negative energy values exothermic. When we think about exothermic and endothermic in terms of energy, if it is exothermic, we think of heat and energy as being a product. And if it is endothermic, we think of heat and energy as being a reactant in that particular case. We then talked about, I believe, specific heat and specific heat capacity. The specific heat capacity is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. And these are the guys that have basically 3 types of units. For example, the specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius, or another very common unit of it is 1 calorie per gram per degree Celsius. That, by the way, is a conversion factor between joules and calories. There's 4.184 joules in 1 calorie. So that's sort of the conversion factor that is used. There's a specific heat equation. Q is equal to ms delta T. Q is our heat or energy. And that's usually joules or calories. M is mass, which is usually in grams. S is our, again, specific heat capacity, which is joules per gram per degree Celsius, or calories per gram per degree Celsius. And delta T is usually in degrees Celsius. It's one of the few things that we do leave in degrees Celsius here in chemistry. And that's because our specific heat capacity is also in degrees Celsius. It's really important when you do the change in temperature that you take the final temperature minus the initial temperature, as mass is going to be a positive number, specific heat capacity will be a positive number. So it really is this sort of change in temperature, which is the only thing that has the possibility of turning your value into a negative number. And if you do get a negative number, that typically means that the process is exothermic. And if you get a positive value of Q, it means the process there is endothermic. In that case. Any questions on any of that stuff there? I think is what we talked about, I suppose. All right, then let's continue on where I think we left off. So we're talking about at this point, for example, bless you, if we have heat being transferred from one object to the next. So for example, if I have some water here, classic water, and let's just say I have 115 grams of water. And let's say initially here, my water's at 26 degrees Celsius. And let's just say I have a piece of metal. And we got like 85 grams of this metal. And we'll say we heat this metal up to like 96.5 degrees Celsius. And I decide that I'm going to toss this metal into this water. And what I want to eventually know is what is the specific heat capacity for the metal. When I throw the metal into the water in this particular case, the metal should get colder, right? And the water should get hotter as heat transfers from hot to cold. So the metal should release all that energy, which means in terms of the metal, it is a exothermic process, right? As it's going to be releasing all that heat and energy to the water. In terms of the water, it's an endothermic process, right? So it's going to basically gain all that heat and energy. So let's just say after we toss it in there, the final temperature of the water goes to, I don't know, we'll go with was 29, why not? That also means that when that piece of metal that's sitting in there, the final temperature of the metal should probably also be 29 degrees Celsius. It should really come to rest at the same temperature, right, as the water does. And that means that we would actually know the final temperature here of our metal, which would be 29 degrees Celsius. So if we see really no heat loss in this case, that there's sort of a nice perfect transfer of energy, in this case from the metal to the water, we could actually use the water to figure out how much energy it absorbed from the metal. So we could do that because we do have the mass of the water, we have our initial and final temperature, we always have the specific heat capacity of liquid water, 4.184 joules per gram per degree Celsius. So for example, if I wanted to use my specific heat equation for the water, I have really all the information that I need. And if I put it in here with my made up numbers, 115 grams, 4.184 joules per gram per degree Celsius, final temperature minus initial temperature in this case, and calculator, there it is. Do a little 29 minus 26. I'm going to pretend there's some zeros on that to give it a little bit more significant figures. Times. All right, so we'll end up with about 1,443 joules of energy, as the grams will cancel, degrees Celsius will cancel, we'll be left with joules of energy. Now, we're ultimately really trying to find the specific heat capacity of the metal. So if we look at our specific heat equation for our metal, ms delta T, we obviously have our delta T. We are looking for the specific heat capacity, and we have our mass. So the one thing that we are missing in this particular case is the heat, or energy there from the metal. And what we know is that all the energy that the water picked up in this case came from the metal. But as we were talking about a second ago, it is exothermic for the metal, endothermic for the water. So the relationship that we have is that the Q of the water will equal negative Q of the metal. The energy should be the same, but the sign should be different. So if we know that the water picked up 1,443 joules of energy, all that had to come from the metal. So we will now know that the Q of the metal will actually equal negative 1,443 joules. It should be the exact same number again here. The sign's going to be different to indicate that it is exothermic for our metal. Questions on that? Now that we have the heat from the metal that we were able to get from the water, we could actually use our specific heat equation again for our metal. In this case, we now can solve for S. S will equal Q of the metal divided by M delta T. So putting in our numbers, negative 1,443 divided by the mass, which is 85 grams. And here it's also really important to do final minus initial. So this is going to be 29 minus 96.5. By the way, that's important because when I do that, what type of number am I going to get? If I take 29 minus 96, I'm going to get a negative number, which is good because that negative and this negative will turn my specific heat capacity into a positive number, which is what it should be. So again, the importance of making sure you do final minus initial. You will obviously get the same numerical value if you just take the difference, but you might end up with a negative specific heat capacity, again, if you don't keep track of those signs. So we'll divide this by 85. We'll divide it by 29 minus 96.5. And we're going to get a specific heat capacity of 0.25 joules per gram per degree Celsius as the specific heat capacity of our metal. So a lot of times we will use water as sort of a source of measurement to figure out what is happening in terms of the water, because we know the specific heat capacity. And this is a very simple sort of experiment that you can do, frankly, with, as we will do perhaps, just some styrofoam cups, basically, and some water, and a thermometer, basically, and a lid. And just by using a thermometer and measuring, again, the temperature difference of water, you're able to really sort of figure out how much energy in this particular example that water absorbed, could also figure out how much energy water would give away as well. It could go in the other direction as well. So it's a very simple way. That's a calorimeter. Is a coffee cup calorimeter, sometimes referred to, because it is usually just coffee cups you stack together because they're very well insulated, no heat sort of lost to the outside or anything like that. It also works, by the way, with reactions. Most reactions, like solutions and stuff, right, are aqueous, which is water based. So a lot of times you can do these type of experiments, actual chemical reactions, and pour them into the coffee cup, follow the temperature change. And you can still use water, since water is probably the major solvent used in most of those solutions, and still be able to figure out how much heat and energy is absorbed. As we will see, when you do that, for example, in a constant pressure situation, the Q value that you get is actually equal to the delta H, or the change in enthalpy for a particular reaction. So you don't really need any sort of fancy equipment to figure out how much energy is being gained or lost in a particular reaction. Now, I personally would recommend, if you have a situation like this, that you do the equations sort of separate from each other, and just do two separate sort of calculations involving um, the specific heat equation using our relationship that we see here. Now, you could, like it shows on this particular slide, know that there's going to be an overall zero in terms of the heat or energy lost. And you can set these guys equal to zero. The importance of this is you got to choose one of these guys and take it to the other side. And when I do that, all those guys are going to become negative. Yeah. So you have to make sure you distribute a negative in there somewhere. Otherwise, you will get the wrong answer. So you definitely could use this, but you do have to, again, when you kind of bring the mass of the metal, the specific heat capacity of the metal, and the change in temperature, for example, of the metal, you got to also kind of distribute that negative across those guys. And then you obviously could have all your of the water, the S of the water, and the delta T of the water. So it doesn't really truthfully matter which side you distribute the negative, but you do have to sort of distribute the negative across that. So if you have the option to sort of do them separate calculations, that's probably the safest way to do it. But sometimes you don't have that option. You do have to kind of put them equal to each other. You just got to remember, again, you got to distribute that negative to give you that opposite relationship that's happening. And the idea that, as we talked about, is whatever amount of energy somebody loses should be the exact same amount of energy that somebody gains. So again, just one's exothermic, one's endothermic, which again is why you need that sort of negative relationship that's in there. Any questions on that there? Okay. All right, so why don't you try one here? We got a 110-gram sample of a metal at 55.5 degrees Celsius. Bless you. Raises the temperature of 150 milliliters of water from 23 degrees Celsius to 25.5. What is the specific heat capacity of the metal? Take a few moments there, see what you come up with. Okay, so let's take a look at this one. So it's basically the same situation as we were just talking about. We got a little thing here of water. We have 150 milliliters of it, which is a volume. We have the initial temperature here of our water at 23 degrees Celsius. After we put the metal in there, it's going to go to 25.5 degrees Celsius. We have a piece of metal that's going to go for a swim here. And we have the mass of the metal at 110 grams. We have the initial temperature of the metal at 55.5 degrees Celsius. Once again, once that metal goes in there, it's going to sit in the water and come to rest at the same temperature as our water will eventually end up. So again, not specifically given to us in the problem here, but we do know from logic here that our final temperature of our metal will actually cool down to that same temperature. We are looking for the specific heat here of our metal. So once again, we are also missing the Q for our metal, but we do have pretty much enough information here for our water to, again, in this case, figure out how much energy our water should gain. We have our specific heat capacity of liquid water, which is 4.184 joules per gram per degree Celsius. We have the volume, but we really need the mass. So we do remember, hopefully, that the density of water, typically, if you need a value for that, is 1 gram per milliliter, right? That means that if I have 150 milliliters of water, times it by 1 gram per milliliter, that is going to give me basically 150 grams of water in this particular case. So once again, here we have everything that we need for the water. So that's where we're going to start. Our Q is going to equal to ms delta T for our water here. Our mass would be 150 grams. Our specific heat capacity, because it is liquid water. Also, a reminder that if you are not dealing with liquid water, you should not use that number. You should actually go find a specific heat of like ice or steam, which is different than 4.184. Our final temperature here of our water, 25.5 minus 23 degrees Celsius. That is going to give us, in this particular case, 150 times 4.184 times 25.5 minus 23. About 1,569 joules of energy. It is positive, as we would expect, since our metal is hotter than the water's temperature to start with. So the heat exchange should go from the metal to the surrounding water. Again, meaning that it is exothermic for the metal, but endothermic, right, for our water, which is why we got a positive number. We also know that the relationship then is the Q of the water will equal negative Q of the metal in this case. That means that negative 1569 joules of energy should have been released from the water in this particular case. And that really is the purpose here in this case of using the water is to really figure out how much energy was released by the metal. Any questions on that there? Now we could go back into our specific heat equation for our metal. And once again, solve for S. And S would equal Q of the metal divided by M delta T, negative 1569, divided by our mass of the metal, 110 grams. And our final temperature of the metal, cooler than it started. And that again is going to give us that negative that we need to counteract the negative that we have here. And that's going to get us .48. None of the units cancel. Joules per gram per degree Celsius, which are the 3 units that we have for our specific heat capacity. Any questions on that one there? So this is a very common sort of process, as I mentioned, using calorimetry, just basically following temperature changes in water, and again, sort of back relating it to whatever caused that temperature change. In this case, it's the piece of metal. Like I said before, you can also do this with reactions as well. Any questions on specific heat capacity? Okay. So we might have talked a little bit about last time as well, but a reminder that there's also another type of calorie that we sometimes come across in terms of energy, and it's more related to nutrition and sometimes referred to as a nutritional calorie, and that has a capital C. And one sort of nutritional calorie is equal to 1,000 of the little calories, and that is also the same thing as a kilocalorie. So this is also a calorimeter is something that's used as well to, for example, figure out your calories in your food and stuff like that. They use a calorimeter and it's sometimes referred to as a bomb calorimeter, something like this. Basically, they put like your chocolate chip cookie in this very well insulated container filled with water, has a thermometer, ignition wires, and they basically set it on fire and do a little combustion reaction. As obviously your food item is burning, is transferring heat and energy to the surrounding water, at which you could do just a super simple calculation like we've been doing, following the change in the temperature of the water. You could figure out how many calories the water absorbed and then change those into nutritional calories. And you can figure out how many calories were given off per gram of a substance as well. Now, when you look at food and stuff like that, and you look at, say, food labels, there's really three types of food that we oftentimes are interested in, and that is carbohydrates, fat, and protein. If you look at any nutritional label on food in a package, you will typically see those three things listed, and you'll typically see how many grams there are of each of those things. Each of these things has what is referred to as a caloric value. And you basically take the grams of each of those guys times the caloric value for carbohydrates, fat, and protein. Uh, for carbohydrates, it's 4 kilocalories per gram, or 4 calories per gram, basically. And for fat, it's 9 kilocalories per gram. And for protein, it is 4 kilocalories per gram. So again, if you look at your nutritional label and you find how many grams of each of those things are, you could use this to calculate how many calories there are, for example, per serving. Anybody have a nutritional label? Candy bar, chips? Kind of college students are you? There we go. Perfect. How many carbohydrates grams are there? 36. And fat? 9 grams. And protein, how much is there? 3 grams. So we would take each of these and basically multiply it by its caloric values. So for our carbs, it would go 4 kilocalories per gram. For our fat, it would be 9 kilocalories per gram. And for our protein, we would do 4 kilocalories per gram. And if we do that there, take a little 36 times 4, gives us 144 kilocalories, or really nutritional calories. 9 times 9 is 81 kilocalories. And 3 times 12 is about 36 kilocalories. You add all those together there, 36 plus 81 plus $1.44. It's about 261 calories per serving. How did I do? Close? They usually round down. 230. They rounded way down on that, I would say, in that case. So in my experience, they usually round down on nutritional labels. I'm not sure why they might do that, but perhaps there might be some reasons why that is. So this is how you obviously could get those values that you see on those labels. All right. So if we look at this, like I said before, a very common way in the laboratory to do sort of energy experiments, oddly enough, is through coffee cup calorimetry. And you could just stack it, like I said, a couple coffee cups together. It's a pretty good insulated type of system. Put a little lid on it with a hole so you can stick your thermometer in there. And you could do these reactions. Like I said, it doesn't necessarily have to be a solid metal into water, but you could do regular reactions. And again, because they are aqueous, you really could still use the specific heat capacity of water in a lot of cases to do your calculations. And as I mentioned a second ago, if you do this under constant pressure, which is typically what you do, the delta H of it will equal the Q value that you get. So for example, if you know how many grams you'd use in a reaction, say a magnesium with hydrochloric acid, you can figure out how much energy, which would be the delta H value. You could divide it by the moles of magnesium and figure out how much kilojoules per mole that reaction gave off by just simply following the temperature change in these coffee cups. All right, let's get that one. The last thing I think we're going to talk about, or one of the last things here in this chapter, is the idea of Hess's law. And the idea of Hess's law is that not all reactions essentially occur in a one-step sort of process. So again, we could have a situation where we have one reaction and another reaction. And maybe overall the reaction that takes place is A plus B goes to E plus F. Here, if we were to add these together, anything that's on opposite sides of the arrow that's the same would cancel out or reduce. So these guys would cancel, and everybody on the left-hand side of the arrow stays there. Everybody on the right-hand side of the arrow stays there. So the idea with Hess's law is sometimes reactions occur in multiple steps. And as long as you know the energy of each of those steps, you essentially can figure out, for example, the amount of energy overall for that reaction by really just adding reactions together. So when we look at an equation such as this, and we add these two guys together, we get the overall reaction of H2 plus a half of O2 gives us H2O. And we could get that by adding these two delta H values together. Now, there are a couple of things that we could sometimes do to equations that does affect the delta H value. So just a reminder that if you had, for example, a delta H of, say, A plus B goes to C plus D, and the delta H is 10. If I did not need the reaction written like that, but perhaps I needed the reverse reaction, that would mean that I need to reverse this reaction. C plus D would give me A plus B. What that does to the delta H value is it changes the sign. So this would be 10 kilojoules, and that guy then would be negative kilojoules, 10 kilojoules. And that is because we do products minus reactants. So if we reverse the reaction, our products become our reactants, reactants become our products, and we change the sign. So if there's ever a situation, especially say in Hess's law type situation here, where you need to reverse a particular reaction, the effect on the delta H value is you basically change the sign of it. So if it was positive, it would become negative when you reverse it. If it was negative, it would become positive. Other things that you could commonly do is perhaps I don't need one of A, but maybe I need two of A. So maybe I need to take this reaction and multiply it all by 2. And if I take 2 times A, 2B, 2C, 2D, how that affects the delta H is you would also multiply the delta H by 2, and that would give us 20 kilojoules for this particular reaction. So if you need to multiply a specific equation by a number, you also would multiply the delta H value by that number. The last thing that you typically could do as well is divide. So let's just say I took this equation here and divided it by 2. If I did that, I would end up back at the top equation, right? And the difference between the delta H of the bottom equation and the top equation is I divided by 2. I also would need to divide the delta H value by 2. So if you have to divide by a common number, you would divide the delta H value by that common number as well. So those are the few different ways that sometimes you can manipulate an equation and the effects on the delta H value. If you reverse it, you change the sign of the delta H. If you multiply by a common number, you also multiply the delta H by the common number. And if you divide by a common number, you divide the delta H by that same common number. When you add a bunch of reactions together, you simply just add up all the delta H values together. Any questions on that there? So the idea of Hess's law is pretty much this. You're going to take a bunch of little reactions, move them around, flip them around, multiply by some numbers, maybe divide by some numbers, that when you add them together, you end up with an overall reaction that you're trying to get to. So for example, here, if we were looking to figure out the delta H for this reaction, and this is ultimately where we want to end up, we want to basically manipulate these equations and move them around if necessary. Sometimes it may not be necessary. So in this case, the easiest way to do it is just to look, and carbon's on the left, carbon's here, it's also on the left, and I need one of each, which means in this particular case, I don't need to do anything. I could just leave this guy exactly the way it was. And that means nothing happens to my delta H in this case. Now, the next thing is CO2, which is on the right. CO2 is on the right, and I just need one of them, which also means in this case, I don't really have to do much to this guy. And I'm just going to leave it the way it is. And that means my delta H here will also remain the same. And now if I did this correctly and I add these together, I should end up with this equation. We will have our CO cancel, and I think that's it. So on the left here, we have 1 carbon. Half and half gives me 1O2 and CO2. My delta H for this reaction then would be just adding these together in this case. We're just going to add both of those together. It's going to give me a 110 plus a 283, both negative, by the way, a negative 393 kilojoules. So in this case, this reaction is exothermic or endothermic? This reaction is, it is exothermic. I got me a negative in this particular case. So let's say that I wanted, though, let's say that I wanted this reaction. What would be the delta H for this one based on these guys? Okay, so let's take a look. So now we want to end up with this equation here. And we're still going to use the other two on the bottom there to do that. So we'll start with the same idea. In this case, though, CO2 is on the left-hand side, and the only place where CO2 is found is in the second equation. It's on the right-hand side. So I know I need to reverse it, and I also don't need one CO2 in this case, but I need 2 of them. So to this bottom equation, I need to reverse it, and I need to multiply it by 2 to give me sort of the right amount of each of those. And if I do that, that's going to give me 2 CO2, gives me 2 CO plus an O2. Now, in terms of the delta H, because I reversed it, it now will become positive 110 kilojoules. And because I multiplied it by 2, I will also need to multiply that by 2 as well. And that's going to give me a 220 on that. Same thing here. Carbon's on the right. It is on the left here. So I do need to reverse that one as well. And I also need to multiply it by 2. So I am going to need to take the top one here and reverse and multiply it by 2 as well. So when I do that to the top equation, 2 CO, 2 carbon, and an O2. Once again, here we reverse the reaction, which means, and I should get the right number in there, I suppose, on the first one. Sorry about that. The first one was actually positive 283, which was that equation. So 283 times 2 is going to give us 566 there. Here, this one's the top equation, so it's going to be positive 110. Also going to multiply by 2, so that will be our 220 here, now that we got them in the right spot. Going to add these together, and our COs will cancel. Gives us 2 CO2, 2 carbon, and 2 O2. It did give us the equation we're looking for. At this point, to give the delta H for this new reaction, we're just going to add these guys together. So that's a 566 plus a 220. That's going to give us a 786 kilojoules in this case for this particular reaction. Any questions on that? This reaction would be endothermic, right? As it's positive, yeah. Is it, say it one more time. I missed the first part to do. Okay. You probably, if your question is, can you just wait to the end and multiply by 2? In this case, you'll be okay, but in a lot of equations, you may, for example, have to multiply the top one by 2 and the bottom one, you don't need to multiply it. So you would get the wrong answer. So it's best to keep each equation kind of separate and then just sort of adjust your delta H for each equation first and then add them together. Yeah. Other questions? All right, so let's try another one here. We want to know what's the delta H of this reaction from these guys. And I imagine one of the answers should be right, hopefully. Look at SO2. This is really the only one that has SO2 in it. It's on the right-hand side, but I really need it on the left-hand side. So I do know for this particular one, I do need to reverse it. I only need one SO2 in each case here, which is what I got. So I'm just going to reverse that first equation. So just simply my products become my reactants become my products. And because I reverse it, really the effect on my delta H now is going to be a positive 297 kilojoules. If I look at my SO3, it's on the right-hand side, which it is over here, but I only need one of them, and I have two in that equation. So that's going to require me to come through here basically and divide everybody by two, which means I also will end up dividing my delta H by two in this case. That will get me an S and a 3/2, I believe, O2, and a SO3. My delta H here is still going to be negative 792, but I will need to divide it by 2 because that's what I did to the equation, and that will get me negative 396 kilojoules. Now to add these together, in this case, S will cancel opposite sides. 1 minus 3/2 is 1/2 O2. So we'll have an SO2 plus 1/2 O2 gives us an SO3, which is what we are looking for in terms of our equation. Now we want to take the adjusted numbers there and add them together. So the delta H for this reaction will be 297 plus a negative 396 kilojoules in this case. So looks like a negative 99 kilojoules would be our answer. Any questions on that one? So this means obviously this is going to be a exothermic reaction in this case. So Hess's law is pretty much that. It's just kind of like a little puzzle that you just got to adjust individual little reactions. The key is to keep track of what you did and how it affects the delta H value, which to the earlier question is why you probably want to kind of do it for each reaction individually. So you could just keep track of what you did to that reaction. So you have the adjusted delta H value. Any questions on that there? Okay. So heat, as we talked about, can be defined as we've been doing, the flow of energy due to a temperature difference. And again, it always sort of transfers from hot to cold. We could also calculate the change in internal energy, which is what delta E is. Q is our heat and W is our work. And a lot of times we do use heat or energy to do some type of work on a system or work done by a system. By convention, heat and work added to a system is positive, but removed is regarded as negative. So again, that's kind of the same idea. Things that are negative are sort of exothermic type processes being released, and anything being absorbed is a positive sort of value. Um, Most processes occur spontaneously, involve some type of energy spread. That means heat flows from high temperature to low temperature. And as we'll talk about in the next chapter, a lot of times we do use energy as a way to look at spontaneity and whether or not a reaction is going to be spontaneous, but it's not really a lot of times the overwhelmingly thing that we look at or use, but it does sort of help us. A lot of times, a lot of spontaneous reactions are exothermic. But there are spontaneous reactions that are endothermic. So you can have a spontaneous reaction that's either and will happen. So let's talk about one last thing here before we kind of move on from energy in this, which is a little tying together of a couple of things about energy and also the energy required to change a phase. of a substance. So for example, if we want to go from solid to liquid or liquid to solid, does that occur at the same temperature or different temperatures? It occurs actually at the same temperature, and that is usually the normal melting point, freezing point of a substance. So, for example, for water, that is 0 degrees Celsius. At exactly 0 degrees Celsius, you have basically both phases in equilibrium with each other. You got like ice crystals kind of happening. You got a little bit of solid, got a bit of liquid. It's not really until you get a little bit above 0 degrees that you sort of fully transition into liquid water. It's not until you get a little bit below 0 degrees that you transition to ice. There is a certain amount of energy required to do nothing more than take a substance at its normal melting or freezing point from, say, for example, water. 0 degrees ice to 0 degrees liquid water are backwards, not changing the temperature, but just changing the phase of that particular substance. That energy is what's referred to as the delta H of fusion, or the heat of fusion. And that again is the energy that is required to, as I mentioned, really do nothing more than just change the phase of it. It will happen at the same temperature. For water, for example, that is 6.02 kilojoules per mole, are roughly 335 joules per gram, is the amount of energy required to do that transition. It is the same amount of energy regardless of which way you're going, but the sign is different because as I go from solid to liquid, is that an exothermic process or endothermic process? If I go from solid to liquid, it is a, if I have an ice cube and it starts to pick up energy, it will start to melt. So if the ice cube picks up energy, that is going to be exothermic or endothermic? It is endothermic, right? So going from solid to liquid would be like positive 335 joules per gram. If I feel bad about my melted ice cube there and I have liquid water, I can do an exothermic process, like throw it back into the freezer, and it would be minus 335 joules per gram. By the way, why is it exothermic if I throw my liquid water back into the freezer? The temperature of liquid water would be like room temperature, right? The freezer's temperature is cold, like 0, right? And that means that when you actually put the water into the freezer, the water is hotter than the air in the freezer. Heat transfers from hot to cold, right? So that is why the water loses all the energy and ends up freezing, right? So it transfers that way. That's an odd thing, like put in the freezer, but it's like losing energy. There's also a transition that occurs, as we know, hopefully going from liquid to gas, right? And gas back to liquid. That's our evaporation and condensation type of situation happening in this case. And same idea, this occurs at the same temperature. That is the normal boiling point of a substance. And for water, that's like 100 degrees Celsius, right? Where that occurs for water. And there is the delta H of vaporization, or the heat of vaporization. And for water, by the way, that is roughly, I don't know, 40.6 kilojoules per mole. I could be making the numbers up, maybe. Or roughly 2260 joules per gram. And again, it's the same idea here. As we go from liquid to gas, that is a endothermic process, right? So as we go from liquid to gas, that's going to be a positive 2260 joules per gram and a negative 2260 joules per gram if we are going in the opposite direction, going from gas back to liquid. Which transition requires more energy? Going from solid to liquid or liquid to gas? It is liquid to gas, right? So if you think about going from solid to liquid, In the solid state, things are typically near each other. Water might be a slight exception on that, but things are typically very close to each other. As you go to liquid, they're still relatively close to each other. As you do that transition of going from liquid to gas, you pretty much need to break everybody away from one another, right, into the gas phase so they can fly around. So it takes a lot more energy always to sort of do that transition of going from liquid to gas. Any questions on that there? So how does this relate to sort of like, say, specific heat that we've been talking about? Let's say, for example, we look at a heating cooling curve here. So let's just say we got a little bit of this and a little bit of that. And let's just say down here is ice, which obviously would be our solid state. Let's say that this is liquid water through this line coming up. And this line up here we'll say is steam, which is obviously the gas phase of water. That would mean that if we shoot across here, this would be 100 degrees Celsius. And if we kind of come across here, that would be 0 degrees Celsius in this particular case. As you can see in this graph, the transition between liquid and gas is a flat line-ish, as flat as I could draw it. And the transition between solid and liquid, also a flat line. Flat lines, right, or plateaued lines means the temperature is not changing, but in this case, the phase is changing. The lines between, say, here, here, and here, those guys are all the same phase all the way through that line, whatever line you're on, and the temperature is changing, right? So from here to here, that is all liquid, right? Temperature changing. And same thing here. This is all gas, temperature changing. And that little bit there is all ice all the way through, just the temperature is changing. So it is a heating curve as we're going from, say, solid to liquid to gas. It is a cooling curve if we head in the opposite direction. So let's just say, for example, we wanted to do this question, which is how much energy is needed to change, we'll go with 75 grams of ice at minus 3.5 degrees Celsius to steam at 102 degrees Celsius. So we want to know how much energy it requires to do that entire transition. Just on our graph, we're basically going to be starting right here in the sunny spot of our graph, about there, at ice at minus 3 degrees, right? And we eventually want to get up all the way up here to, we'll call that 102 degrees Celsius. And this is our minus 3.5 degrees Celsius. There is a lot of steps that sort of occur for us to get all the way up there. And it does happen in parts. The very first thing that would happen in this case is we would have to take it from ice at minus 3.5 degrees to our first transition point, which is ice at 0 degrees. So that would be the first step that would have to happen. We would have to go from ice at minus 3.5. I'll do it on here. So our very first step, we would take ice at minus 3.5 degrees Celsius to ice at 0 degrees Celsius. Remember, 0 degrees Celsius is where we're going to have our phase change. So we can't do our phase change until we get there, right? So this transition right here is ice all the way through, which means it's solid all the way through. And the only thing that's changing is our temperature. So when you have a substance that's in the same phase and you change the temperature, we know how to figure out the heat. It is the equation we have used previously, which is our specific heat equation. That is the equation that you would want to use where the substance is in the same phase, but changes temperature. So if we do that, we can put this in for our very first step, which would be 75 grams of ice. Also really important, At this point, this is ice and not liquid water. So you would actually want to use the specific heat capacity for ice, which is roughly, I always get it backwards, but I'm going to go with my best guess here of 2.03 joules per gram per degree Celsius. So you would not want to use the 4.184 number here because that is for liquid water. And we're currently sitting with ice. So we haven't got to liquid water yet. So you want to make sure you use the right specific heat capacity. That would be 2.03 joules per gram per degree Celsius. Final temperature here is 0. Initial temperature, negative 3.5 degrees Celsius. That is going to get us here for our very first little part. 75 times 2.03 times basically 3.5. That's going to give us, we'll call it 532.9 joules of energy. So that is the amount of energy required to take our ice at minus 3.5 degrees and kind of raise the temperature up to 0 degrees Celsius. Any questions on that so far? All right, the next thing that's going to happen is if we kind of go back to our little graph here, we're not at 0 degrees Celsius, right? And 0 degrees Celsius is where we're going to get a phase change occur, right? So it's where we're going to go from ice, which is solid, to liquid water in this case. So the next step that's going to happen is actually this transition right here, and that is a phase change, and that is our solid to liquid phase change where we use the delta H of fusion to do so. This is a part where the temperature doesn't change, but the phase changes. So if the temperature doesn't change and the phase change, you do need to use something like the delta H of fusion in this case to do that. So that is the next part of the process here. We're going to take it from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. That's a phase change. And that's a delta H of fusion that we use to do that. I'm going to use the joule number that I put up there. So we're going to take our 75 grams of ice, or we're going to times it by the heat of fusion for water, which is 335 joules per gram. And that will get me something like 25,125 joules. That is the amount of energy to do nothing more than take that ice that's sitting at 0 degrees and transform it to liquid water at 0 degrees, not raise the temperature. Any questions on that so far? So now we are sitting with liquid water at 0 degrees. Remember, we want to end up at steam at 102 degrees. So the next sort of step that we need to do is, if we look at our graph, is essentially we need to go from 0 degrees liquid water all the way through this orange, and all the way through that orange is liquid water, to 100 degrees liquid water, which is really the next sort of transition point of phases that we need to go through. So this is a situation where we are going from liquid water at 0 degrees Celsius to liquid water at 100 degrees Celsius. This is a situation where it is the same phase all the way through, but the temperature changes. So this is again where we go back to our specific heat equation at this point. So going back to our specific heat equation, our Q is going to equal 75 grams. We are now at liquid water, which means we can use the specific heat capacity for liquid water, which is our 4.184 number. So we'll use that. Final temperature 100 degrees, initial temperature 0 degrees. And that's going to give us about 31,380 joules of energy to do that transition. So that's the amount of energy needed to take our liquid water at 0 degrees all the way up to liquid water at 100 degrees. Any questions on that so far? Now I am sitting at liquid water at 100 degrees. I want to eventually get to steam at 102 degrees. In order to do that, if we look at our graph, wherever my graph went, I am sitting right here. What do I have to do to get over to steam? I have to do another phase change, right? I got to take it from 100 degrees, which is the normal boiling point of liquid water, to 100 degrees of steam. So this is going to be another phase change that's going to occur at 100 degrees Celsius. That is where we will use our delta H of vaporization in this case. So the fourth step here is our phase change, 100 degrees liquid water to 100 degrees steam, our gas. And that again is our phase change. And that is our delta H of vaporization in this case. I again am going to use the joule number since that's what everybody else is in. So 75 grams. Heat of vaporization for water, 2260 joules per gram. Cancels out. 75 times 2260, about 169,500 joules required to take it from liquid water to steam. Now, we talked about it earlier. Takes a lot more energy to do that transition, right, than it does to do the previous transition, right? Previous transition from solid to liquid, about 25,000 in this example. Transition from liquid to gas, about 170,000, right? So that's a pretty big difference in terms of the energy required to do that. At this point, if I look at my little graph, I am sitting here. I have one last thing to do. I now need to take it from steam at 100 degrees to steam at 102 degrees. And that would be the last part here. We're going to take it at steam 100 degrees Celsius to steam at 102 degrees Celsius. That is the same phase, but different temperature. So once again, back to our specific heat equation. We do need to use the specific heat for steam, which is about 2.01 joules per gram per degree Celsius. So we'll put it in there. Q is going to be 75 grams. The correct specific heat capacity for steam. Final temperature 102, initial temperature 100 degrees Celsius. And that's going to get us here 75 times 2.01 times 2, basically. About 301.5 joules. Questions on that so far? We have now did pretty much the 5 steps that would be required to take ice all the way to steam. The total energy would be found by doing what with all those numbers? Yeah, we're just going to add them together, right? So all those Q numbers that we got, we're just going to add them. And in this case, that would be 532.9 plus 25, 125 plus 31380 plus 169500 and a 301.5. Going to get us something like 226839 joules, are roughly 227 kilojoules of energy in this case if I divide it by 1,000. This is a endothermic process or exothermic? This is all endothermic, right? They're all positive all the way through, which makes sense. First off, any question on any part of the calculation? What would be the only difference if I started at 102 degrees steam and ended at ice? What would be the only thing that changed in all these numbers? Yeah, it would all be negative because it's exothermic, right? So if you're going in the opposite direction, these guys would change, which would be negative. This guy would be a negative. These guys would change, which would be a negative. This would be a negative. These guys would flip around and become negative, and you would end up with minus 227 kilojoules of energy if you went in the opposite direction. Any question on that relationship there for heat of fusion, heat of vaporization, specific heat? So the take-home message is sometimes if you have these type of problems, a little graph like this is helpful. Anywhere the graph kind of goes upward and it's the same phase but different temperatures, specific heat. Anywhere where you keep the temperature the same but change the phase, delta H of fusion, delta H of vaporization. Any questions on that? All right, that wraps up chapter 7.